Last time we talked about force fields in general. We're going to do something similar now with the electric field. In the last lecture, we calculated the force due to electric charges, and that force depended both on the charge that was causing the force, the agent, and the force that received the charge that received the force, so the object, right? So what we're going to do in this case is divide by the charge of the object in a hypothetical scenario. And so all that it's going to depend on is the charge of the agents and where they are. And what we're going to be left with is what we call an electric field. And so we're going to be able to calculate an electric field strength. And just like this is newtons per kilogram up here, this is going to be newtons per coulomb because we have a force per charge. And so we only care about the agents of this. So we call these source charges. And we don't care about the charges that would hypothetically feel these electric forces. We call those test charges. They're ones that we just think about putting in the electric field, but we're not considering that we actually do put them in. Right? So let's calculate, or let's first draw a scenario where we have something like this. So let's say that we have a positive charge in the middle. Right? So this is a positive point charge, and we're going to think about what the forces look like at different points around it. So we'll do kind of like how we drew for the Earth. We'll do these points, and these are supposed to be equal distances around these four, and these other next four are supposed to be equal distances away from the point. So we know that the force on a charge depends on the distance. So think for a moment that we have a test charge right here. And these test charges we always think of as positive, right? So we, for the moment, think of a hypothetical test charge, and we think of what the force on this hypothetical test charge would be. Well, this is definitely positive. So the positive test charge would have a force pointing away on it. Okay? But now we get rid of that test charge. It was imaginary. It was never there. And we do the same thing at this point, right? It's the same imaginary test charge, but now we are approximately twice as far away. So we're going to have a smaller force pointing away. If it's twice as far away, we know that it should be 4 times shorter. And we can do the same thing at all these other points, right? It's going to point away. That's going to be smaller. This is going to point away. That's going to be smaller. Point away. This is going to be smaller. So something like that. And indeed, we could continue this at all the other directions, and we could just draw as many of these as we need in order to understand what the electric field looks like around a positive charge. So this is one of the most fundamental to understand. A dipole is a little more involved to understand, but I'd like us to at least take a look. So with a dipole, what that means is that we have a positive charge on one side and negative charge on the other side. The amounts of these charges are supposed to be the same. So this is a positive charge Q, and this is a negative charge Q. By the way, these are both source charges, so these are real. And we're going to consider what happens to a test charge that we put at various points. So we can have a test charge here, and here, and here, and here, and here, say, and we'll do one here, and here, and let's make that a little closer. That will be good enough for right now. Okay, so let's look at this one first, right? So this one, remember we're thinking of positive test charges. This one is going to be strongly repelled by this positive charge. There is a negative charge, so it's going to be attracted to this negative charge, but that negative charge is very far away. So it's not going to be strongly attracted to that negative charge. So the overall result is going to be repelled in that direction. Now, if we look at this one, this positive test charge, right, we can get rid of them after we've looked at it. It's going to be strongly attracted to the negative. It's going to be repelled by this positive, but the positive is very far away. So we're going to have a strong left on that one. Okay, now let's look in the middle. Right here, we have a strong right and a weak right. So the overall result, we might have to draw it slightly to the side so we can see it, is a pretty strong right. At this point, we have a strong repelling force and a weak attracting force to the negative charge. So the overall result is an overall right vector. In the middle, we have a medium right, so a repulsion from the left, and a medium attraction to the right. So there's also a right pointing vector. So all along the middle, we have an electric field pointing towards the right. Let's think about this one. We might need to draw more vectors on this one. We have a repulsion that's down and to the right, and an attraction that is up and to the left. Right? This test charge is equally spaced between these two, so the overall result will be directly to the right. Similarly, up here, you can see by symmetry it has to be the same thing. There are many more points we could do on the dipole, but we will leave it at that.